Hello everyone, a short video to show some of the work that I've been doing within the geometry as code project in Blender. This one is simply an experiment to see if it was possible to convert an OpenSCAD program, so basically a program that describes geometry through constructive CSG, constructive solid geometry. And I wanted to see if it was possible to take such a program and convert it to a tree of Boolean operations and primitives in Blender. All right, so let me show you how that goes. I've actually published the code on GitHub here. You can see it here, Motion A, SCAD2nodes. So let me show you what it does. I think it's simpler than trying to explain it with words. So I'm going to clone the repo. There we go. And within the repo, you basically have a bunch of example models. Let me show you what they look like in OpenSCAD. So if I, for example, launch OpenSCAD on a model called hull.scad, you will see it's basically a box with rounded corners. There you go. Which, yeah, looks like this. Okay, here's the code. So fairly simply, it creates a sphere, which is one of the corner of the box. Then it takes two spheres and moves them along the y-axis. And then it takes this so-called edge and creates two of them to make a square. Eventually takes two squares to make a cube. So essentially this is four little spheres positioned at the vertices of a cube, and then applies a convex hull operator to the result, and that creates the object you've just seen. All right. I'm going to so here's what I'm doing is basically running make to compile a little parser that's capable of parsing the output of OpenSCAD. And then I use OpenSCAD to convert my little program, the little program that you saw just now, into what's basically the equivalent of AST for OpenSCAD. So let me show you what that looks like. Right, it sort of inlines all the operation, right? So you go from this, which is a rather concise description of a geometric object, to this, which is basically the same program but with much more detail and all the for loops and function calls and everything unrolled, so to speak. All right? And then my little parser converts this. This is basically a CSG tree, an AST that describes a CSG tree, constructive solid geometry tree, right? It has primitives, it has transforms, and it has Boolean operations. And at the top, the convex hull operation. Okay, my little parser that you see in action here consumes this unrolled description of the constructive solid geometry tree and converts it into a small Python program. It looks like this, right? It creates a node, which is a sphere, another node, which is a transform that is being applied to the first node, and so on and so forth. So it basically describes a tree of geometric nodes. And then there's a little bit of Blender Python that takes that node-based description of the CSG trees and converts it into native Blender geometry trees. And if I execute this, this is what it looks like, which is nice. It looks more or less like the object in. All right. So what we're looking at here is basically Blender. We have an object with a geometry node modifier, which you see here. that has been all of this has been automatically created by the little Python script that I just ran. Right, let me do it again to make sure you get what just happened. I'm going to run a Python script, right? This Python script basically is Blender Python, right? It's particular using all the native Blender Python code to do things. It's going to open this, right? And this essentially tries to map the geometric primitives of OpenSCAD to native geometric primitives of Blender. All right, and when I launch this code, it launches Blender and calls internal APIs of Blender, Python APIs of Blender to essentially create an object, create a geometry node modifier, add nodes to the tree, connect them with one another, etc., etc. All right, it all happens behind this. So here's the result, right? The tree is not laid out, so you can actually use. There is a. Sorry for the aside. There's an add-on called arrange. Yeah, node arrange, right? Which, if you want to play with this, you had better activate. It comes with Blender, but it's not activated by default, so you have to basically turn it on. And essentially, the node tree that's here is all piled up on top of each other. But if you say arrange all node, the little add-on I spoke about basically unwraps everything. So here's our object, right? It's it starts with a sphere, right? Applies 2 transforms and creates a union. Actually, we could see exactly what this subtree does. You know what? I'm going to show you the code, the original OpenSCAD code on one end, and the thing we're looking at in tree form. Where is it? hull.scad. Right. Okay. So essentially, if you look at this, let me minimize. If we look at the tree here, right? You see this node here, right? Corresponds to this piece of code here, right? And then this piece of code, we applied one translation, another translation to this. These are our 2 transforms right here. And then we apply a union to it, right? This is the union. Now, if we want to see what that looks like, we need to bring this guy here, the group output, closer. Right. Okay. Can hide this. So if I want to see the output of this union here, all I need to do is plug this into this, and we see our 2 spheres, right? Now, these 2 spheres, a new object. Again, we apply 2 translations to it in the union, and this gives us sorry, clumsy with this UI, right? This gives us our 4 spheres, which in turns are again plugged into the 2 transforms in here in order to basically make 8 vertices. So this again, there we go. So we essentially have 8 spheres, and then this gets fed to a convex hull operator, which is going to create a box. Sorry. Here we go. All right. Let me rearrange all of these properly. Voila. Okay. So this again, now we have all the pieces in front of us. Let me show you all the steps. So you start with a small piece of OpenSCAD code, right? Called hull.scad. The resolution is a little high for OpenSCAD to do this quickly. Right, here it is. Okay. You convert it from the piece of code you see here. We feed it to OpenSCAD and ask it to show us the raw CSG tree, right? Which looks like this. Then we feed it into my little C++ parser, which is, you know, just parsing the EST and converting it to this little chunk of Python code, which can then executed by Blender in order to produce these things. Voila. Okay, so this is, by the way, not, this is just an experiment. Like, I haven't implemented all of the OpenSCAD primitives in Blender and all their possible arguments and specificities. This was just to see what it would take to actually implement a native execution of an OpenSCAD. What I mean by native is the geometry engine within Blender executing the operation that you describe with OpenSCAD, whether it would be as robust, whether it would be quicker. It is definitely quicker because Blender's Boolean operations are very, very fast. They're not as robust as those found in OpenSCAD that use a geometry called CGAL. But when it comes to interacting with the software in order to get quick results to see what's going on, it's much faster than the native solution. Yeah, that's basically it. Let me show you maybe another couple examples of things I've done with this. Here's, for example, something called dodecahedron.scad. So where you see something that creates a dodecahedron, which is you know, not a necessarily easy object to build. It uses again the convex hull operator, and then it instantiates a whole bunch of them. So if I show you what that looks like within OpenSCAD, this is what it looks like. Right, it creates one dodecahedron and instantiates it a whole bunch of times into one big union, and finally punches a hole in the center with a cylinder, right? This is the code. You see here the module that creates the dodecahedron. You see here the something that creates a vector random rotations, and then the thing that creates in a whole bunch of instances of the dodecahedron using a for loop. And then finally the hole in the middle, and the final object is the walls made of dodecahedron punched with a hole. Right. If you want to look at the CSG file, it's a pretty large affair. Right, because all the for loops, all the function calls have basically been completely unrolled. It's 4,000 lines. If you look at the corresponding Python piece of code, it's also very, very large. It's got 112 nodes. And this is actually one of the reasons why I'm working on this geometry as code project. There are some objects describing them with a tree of nodes is just going to be humongously large, right? Because you don't have for loops, because you don't have recursive function call when you work with raw nodes. So there are situations where being able to describe an object with code in a parametric manner is actually better, because if I show you what this object looks like in Blender, it gets a bit scary. It's going to take a while to load because Blender is trying to, actually not that bad. So good thing the object actually looks the same in Blender as it does in OpenSCAD. And then of course you got all the benefits of the very sophisticated UI that Blender offers to interact with 3D object, which is, in my humble opinion, much better than what you have in OpenSCAD itself. But the tree is, and just the layout algorithm is going to take forever simply to lay it out because it's very, very, very big. Yeah, very, very, very big. Right? This, so actually my system is smart enough to detect identical nodes and then sort of like, you know, for example, the dodecahedron is this, right? It's a cube that's moved a whole bunch of places and then fed into a union and then into a convex hull. And it's my code's, you know, capable of detecting similar subtrees and then essentially collapsing them into a single one. So all of this here is the dodecahedron. That should actually be fairly easy to see if I move this guy here. Right. That's before the convex hull. This is essentially a cube moved into very many different positions, and then when you feed it to a convex hull node, this is what you get. Dodecahedron. And then said dodecahedron here is then fed to as many transforms as are required to instantiate it, you know, n times where n is arbitrary because it's essentially described in the code. And all of these instances are then fed back to a giant union, which looks like this. Takes a while. When you ask Blender to compute very large, a union of very large number of objects, it's not, you know, instantaneous, but it's actually quite fast. Voila. And then all that's missing is the hole in the center, and that's this guy here. Where's the other guy? Ooh, it's lost at the bottom. Yeah. Again, you know, it's proving my point that getting this, if you actually create geometry node trees using code, it's gonna get very, very large, very, very quickly. And it's not the best paradigm to manipulating that kind of objects. You know, if you will, one way to look at this is comparing this humongous thing with this, which is essentially the same thing, right? This is 50 lines of code versus a very, very large tree, one with which you can't do much. It might actually be a good place to explain why I'm doing this, right? My goal here is not to create a system that can convert a piece of code into an actual geometry, a tree of geometry nodes, but rather, or not one that the user would ever see or would ever interact with directly. These are just going to be way too big and way too unwieldy to do anything useful with. However, I wanted to see if we could directly execute OpenSCAD code using the geometry engine built inside Blender, the native geometry engine of Blender, instead of using the OpenSCAD geometry engine. And one way I've chosen to do it is by creating these trees. But if I ever use this method in the Geometry as Code final project, this tree that you see here, which is really big and fat, will be completely hidden from the user, unless the user, you know, wants to sort of bake it and start playing with it manually later on. Let me see, what other things have I done with this? Thingy, text. Yeah, I can show you thingy, or maybe, oh, here's an actual object. It's a door, basically, with a model. So if you look at the, again, OpenSCAD code, it's, you know, something that describes a door using code. And if you look at the object in OpenSCAD, looks like this, right? And that's the object, right? And if you look at, if you try to, you know, play with this object using this SCAD2nodes code, this is what that's gonna look like. Again, here's the tree. Let me sort of lay it out, right? And so you basically have a whole bunch of nodes applying operations to primitive in order to create the final geometry, which looks like this. Voila. I think that's mostly what I wanted to show today. Yeah, there's one minor interesting technical detail that you know, people looking at this from a compiler background might find interesting, but there's a point in the process where, remember, you go from this, which is a short piece of code, to this, which is sort of the unrolled AST of the code, right, to a bunch of nodes, right? It's a tree of geometry nodes described in textual fashion. The thing that does the conversion, so ask OpenSCAD to execute the OpenSCAD code and produce the CSG tree. Use my little piece of code to convert the CSG tree to the Python description of the tree, right? If you look at the code, it does a couple of things that aren't entirely trivial. The first one is to remove dead code. There's a whole bunch of parts of the AST trees that are never actually used, so that this gets trimmed. There's a whole bunch of places where you apply a whole bunch of transforms serially, right? And instead of creating 10 nodes, one of which applies a translation, another one a rotation, another scaling, etc., and creates very, very large tree, these gets concatenated. All the matrices get multiplied into one big transform node. That makes slightly smaller trees. And finally, there's this stage, which does just try to discover similar subtrees and collapse them into one, right? Actually, that's a good thing to try. If I remove the compression part of it, remember what the hull looked like, right? cp hull.python z.python, right? If I launch it, you will see that similar, right? You see that there are portions of the tree that have been recognized as identical, like these, and then collapsed. If we turn off the tree compression or identical subtree recognizer, if we turn it off, and oh, it's already copied. Yeah, we have what, 3, 6, 9, 12 nodes here, right? Now we have 30. It's almost tripled. And if you look at the result, you will see that there is very little in the way of there's nothing at all, as a matter of fact, in the way of collapsing identical thing. The 8 spheres are instantiated and baked. All the transforms, all the unions, the tree is much larger. On the other hand, it's not a DAG anymore, which is nice. It's a pure tree. It doesn't have these things where, you know, one node feeds multiple nodes. You're almost guaranteed that there's no one node going into multiple nodes downstream of it, I think. Anyways, okay, I think that's pretty much all I wanted to say. The conclusion of this is not something that's useful in any way yet. This is just an experiment to see, you know, what could be achieved. Whether this is going to make it in the final Geometry as Code project, that's TBD. But it's kind of fun. It's also a good way to understand sort of the relationship there is between a domain-specific language like OpenSCAD, which is really dedicated to describing geometry as concisely as possible. The sort of Unroll AST or you know, geometry tree that it converts into, how you can sort of massage this with code and import this into Blender in order to create what you know, well, to automatically create geometry trees, right? By the way, if you want to sort of load test what the geometry nodes are capable of in Blender, this is a nice tool because you can generate like massively large objects with this. It's just a matter of, you know, tweaking a couple of variables in the code and making things that are going to be very large. Trying to think if I have something in there that could do this. Alright, let me reactivate the tree compression here. Right. So if we look at this thing called thingy.py, what does it look like right now? Yeah, so it's basically a bunch of drilled spheres that are you know, instantiated and then merged with one another. Oh, by the way, there's a nice thing in this. This is, you know, a full-blown Blender geometry tree, meaning I can go and tweak it manually if I want. For example, the spheres are very rough right now. If I decide to move them to, say, you know, finer resolution, takes a little bit of time, but Blender eventually cranks out the slightly nicer object. Eventually. Yeah, these are Boolean operations, they're not cheap. Alright, but the tree is still reasonably small. If I wanted to make a very large tree, all I have to do is go in the code. And then here I have essentially 5 sphere. Let's make it 50 or 500, whatever, right? And you will see that the resulting object takes for a while to compute, but more specifically, the tree of nodes starts to get very large. Yeah, I don't think I'm going to let it finish because, oh, right, well, Blender is an amazing piece of software. You can see that there's 50 spheres here, or drilled spheres. Although there seem to be some missing in the middle. Yeah, interesting. It might be a bug in the Boolean resolution engine in Blender. Yeah, I think there's that's a bug. Interesting. Anyway, what I was trying to say is, if you look at the size of the tree, it has grown quite fat, right? So if you want to push the geometry node subsystem within Blender to its limit, this is very easy to do it with. Okay, folks, I think that's all I wanted to show you today. It's already a long video, I think. Enjoy!